Right, so we can continue with this, and we have got our GCD. So the solution, um, we can write 11 times 1 plus 5 times negative 2 is equal to 1. But what we want to solve is C is equal to 7. So therefore we need to multiply by 7. So we get 11 times 7 plus 5 times negative 14 is equal to 7. And then compare the two equations that we need to solve, um, this and that, and we can find our x value to be equal to negative 14 comparing these two equations that's here, because those are the two equations we wanted to solve. So we have comparing x equals negative 14. So that's our solution for x. If x is negative 14, then we can find our y value. So if x is negative 14, your y value is going to be so therefore n is going to be 5 times negative 14 plus 2, so that's going to be negative 68 from 1. From this equation that's here, you can see that it's 5 times x plus 2, that's a negative 68. But we want to solve this in modulo 55, therefore n is equal to 42 in mod 45. Mod 55. So our final answer, n is equal to 42. Because negative 68 is related to 42. You can see that if you add negative 68 plus 110 will give you 42, because we want to try and find the principal modulo. So negative 68 plus 110, so plus 55 plus another 55 will bring you into 42. So negative 68 is related to 42. So 42 is your answer, and of course you can check that 42 will work for both equations, and that's your solution. So that's how we solve Chinese remainder theorem problems. Okay, that brings us to solving another type, non-linear congruence equations. Um, Again, if you want to solve an x square equals 1 in mod 8, now in this case 8 is a small number, so I know that x can only take these values, and then when I square them I will see that x square can only take these values. For 3 square is 9, 9 is related to 1 through mod 8, and therefore you can see that we have 4 solutions for x. It can be 1, it can be 3, it can be 5, or it can be 7. So that's fairly easy to solve. We can also look at more complicated nonlinear equations. It all comes down to reducing. So suppose I want to solve this equation in mod 5. Now I know that x can only be one of these 5 solutions, but with large numbers we will use Fermat's theorem. A to the p minus 1 is related to 1 in mod p when p is a prime number, as in this case we are solving it in mod 5, which is a prime number. So Fermat's theorem tells me x to the 4 is 1, and I can use that to reduce the x to the 47, 47 is 44 times and 3. 44 is 4 to the 11. 4 is 1, so 1 to the 11 is 1. So for x to the 47 is equal to x to the 3. So this is equal to 1. And also I can reduce the 36 because 36 in mod 5 is related to 1. 36 is 35 plus 1. So 36 is related to 1, and I can use all that. And you will also notice that 5 is related to 0. So I can use all those properties to reduce this equation. So finally we can reduce this equation. This becomes x3, modulo 5 is 0, so I don't need to consider that. and I can solve it, bring everything to one side, just like how you solve equations. Negative 1, of course, if you want, you could have written this as 4 if you wanted, and then you can, now it's a simple equation, we can use trial and error and try x equals 0, 1, 2, 3, 4 and see what we get. Unfortunately, there are no solutions to this equation. Next we have an application of what we learned used in modern day banking and online transactions called the RSA method. It was discovered by Rivest, Shamir and Edelman, three mathematicians working on it. It's used for encrypting the data. Suppose you make an online transaction and you give your credit card number, and that credit card number is first coded and encrypted before sending it to Visa. And then Visa will have to do the reverse, uncode it to find your credit card number. So in the transaction, this coding and the uncoding has to happen. So we use one process to code and then another process to uncode. So this is the way it works. So this is the coding method, the encryption method. If we take two large distinct primes, and in these examples we are looking at really big, large, prime numbers, and unfortunately it's not possible for you to do it with manually. You will need a calculator, computer, because we are talking about really big numbers. So anyway, if you find two large prime numbers, we take n to be the product of these two prime numbers, and now we need to find an integer e, so that will be co-prime with this p minus 1, q minus 1. Now p and q are prime numbers, but p minus 1, q minus 1 will be composite numbers. So we need to find a number e which is co-prime, so that they don't have common factors with p minus 1, q minus 1, and also we want e to be a smaller number than that. So we want to find a number e which will be co-prime with that. And then what we want to do is, once you find this number e, find the inverse of that e. So this is what we were looking at, e and d. They should be inverse, multiplicative inverses. E times d should be 1, so d is the inverse number. And we want to solve this in mod p minus 1, q minus 1. And once you find this number d, and you need to make sure that d is also smaller than this p minus 1, q minus 1. So we know how to solve the inverse equation, and we can find d. And then e and n is the public key. That's what's given to the teller, to the banks, to all that. D and n is the private key. That's what Visa or MasterCard, the account holders, will keep. They keep the solution, the inverse d, and give e to the retailer, to the place where you give your credit card. So how this scheme works is that suppose M is the message that has to be transmitted. It can be the credit card number. So when you go to a retailer and you give your credit card, and they put it into the machine, and the machine will find this number, your credit card number, and then first encrypt it. So they have this e in the machine built in. So they are going to use put M, this number you got, to the power E and get this number C. And this is the number C that's sent to Visa. And C is the encrypted number. So they don't send you the credit card number, they send C. Because it's the credit card number everybody can see, but when you encrypt it, they send instead the number C. And then when Visa or MasterCard or whoever the service provider is gets this C, they use C to the power D and get the number R. This R is going to be back to this number M. You can see it in a moment. So once they get C, use C to the power D and get this R, and that R is to open the encryption. Because then you are going to see that M is equal to R, because R